Welcome to today's webinar. The topic today is partial internal forces method in RFEM 6, economical approach to steel design. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Niklas Wanke will be the presenter today. He works in the customer support team and is also responsible for the development of the add-on steel design. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and then I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Niklas. Niklas, you can start.
Thank you, Andreas, for the introduction. Now let's have a look at the content for today's webinar. In the first step, we will have a look at the theoretical basics of the partial internal forces method. Next step will be to switch to RFEM 6. There we will see how we can use the partial internal forces method, short PIFM, in RFEM 6, what input is necessary and how the results will look like. After we have finished that, we will do a short comparison between the PIFM and the EC3 design checks. And last but not least, I will give you a short summary about what we have learned after the webinar. Okay. Let's start with the first point, theoretical basics. We start completely at zero, and maybe the first question you may ask is, what is the partial internal forces method? This is a verification method which can be used for steel design, so for the steel construction sector. This method is a design check, and especially it is a plastic cross-section design check. So we can use it for steel members, and we can design these members with their plastic reserves. This method, PIFM, has been developed in Germany at the Ruhr University Bochum, mostly by Rolf Kindmann and Jörg Frickel. Next question you may ask is, okay, now I have a basic idea what this method is, but why should I use it? Because we also have the Eurocode design checks for cross-section, or also in other standards we have design checks to design the utilization of members. So why should I use the PIFM? And in my opinion, there are two reasons, and that's already enough, because these are two arguments that are really strong in my opinion. The first one is that the PIFM is almost universally applicable. We will talk about the application limits later. There are some, but overall the PIFM can be used in many cases where the plastic design checks according to the standard cannot be used anymore. And the second reason why the PIFM is very interesting is because in many cases we can reach a significantly more economical design compared to the EC3 design checks, or also design checks in other standards. That means that we can reach a lower utilization together with the PIFM. Good. Now we know that this has some potential, but how about admissibility? Am I am I allowed to use this method because it's not mentioned anywhere in the standard? And yeah, to answer this question, I have also 2 points. And the first one is, if we have a look at the Eurocode 3, we can see in EN 1993 11 in the section 6.2.16, there is some statement about the plastic design checks. And here the standard says the plastic resistance, the plastic resistance of cross sections should be verified by finding a stress distribution which is in equilibrium with the internal forces and moments without exceeding the yield strength. This stress distribution should be compatible with the associated plastic deformations. So this is a general statement made by the standard, and it says that if we do plastic design, there are mainly 2 conditions. The first one is that we have an equilibrium between the internal forces and our stress distribution. And the second condition is that the stress distribution should be compatible with the associated plastic deformations. And these 2 conditions are completely fulfilled by the PIFM. So this means that if we use the PIFM, we are in accordance with this sentence or of this condition made by the standard. So this means that the PIFM is admissible according to the Eurocode 3, and also according to other standards. It always depends on the restrictions or on the conditions that each standard makes. And the second point, which may lead to more confidence when using the PIFM, is that this method is especially mentioned in the German Eurocode 3 comment. And here they say, they mention the PIFM, and they also say that this is a useful method or useful alternative to the plastic interaction checks that are given by the standard. Okay, now we know some basics about the PIFM and what it is. Next step would be to have a more detailed look into this method and how it works. So for that, we will have a look at the PIFM with redistribution, which is, let's say, the most common or the classic method. And this method can be split into 5 steps that we have to perform to use this method. And we will go through it step by step. And the first step we will have to do if we want to use the PIFM with redistribution is that we have to do a transformation of our internal forces from our original coordinate system, which would be the UV coordinate system, like for example for this member or cross-section here. So this is the U axis and the V axis. And we have to transform these internal forces that we receive from the static analysis to a reference coordinate system, which would be U-V- in this case. There's a basic rule or assumption, which is that our reference coordinate system is always located in the center of our cross-section web, which would be like here on this location. And the axes U- and V- are always horizontal and vertical. So horizontal and vertical to the parts of the cross section. Okay, and you can also see the transformation in this figure here. So we have our original internal forces, and they have to be transferred to our center of the reference coordinate system, which would be this one here. Okay, once we have done this transformation, we can proceed with the next step for this method. And this next step would be the conversion of internal forces into partial internal forces. And yeah, this is also the clue of this whole method, or yeah, the point that gives this method its name, because it's named partial internal forces method. And here we calculate these partial internal forces. So the idea of this method is to split such a complex unsymmetrical cross-section into multiple rectangular parts. And I think for this cross-section, it's very obvious that we will receive 3 parts, which would be the upper flange, which is a rectangular section part, the web, and also the lower flange, which are all rectangular section parts. And for each of these parts, we calculate these partial internal forces. So this means if I have a normal force, for example, on my whole section, then each part will receive a smaller part of this whole normal force as partial internal forces. Same for all other internal forces. We can calculate these partial internal forces by using the equilibrium conditions, because as I said before, this is one condition made by the standard. We have to fulfill the equilibrium between the internal forces and the stress distribution. So we can use these equilibrium conditions, which show the reference between the original internal forces and the partial internal forces. And by transforming these formulas, we can easily calculate our partial internal forces for each internal force and for each part of the section. Okay, and if we have finished that, we can finally start with the design check. And this design check starts with the verification of shear internal forces. So these are all internal forces that lead to a shear stress, which would be the primary torsional moment, our shear forces in both directions, and also the secondary torsional moment if we are in a 7 degrees of freedom system. And yeah, based on these shear internal forces, we can calculate, or first of all, we do the design check based on these forces. And the design ratio of this check will be used to reduce the yield strength. And with this reduced yield strength, we go to the next step, which would be the verification of our normal stress internal forces. So normal stress internal forces means we have our bending moment about z-axis and our warping by moment. And both these internal forces will lead to a flange bending. So if we have a look at the flange, our z-axis will be located in vertical direction. Then we can see that mz and omega will both lead to a bending moment in our flange, in the strong axis of this flange rectangular section part. Yeah. So we do the design check for these two internal forces, which lead to normal stress and normal stresses. And we do this design check, as I said, or as I mentioned, with the reduced yield strength we got from 0.3. So, by the way, if in 0.3 we already receive a design ratio that is bigger than 1, then it's over. So then the design check is not fulfilled for the whole PIFM. Same if we proceed with step 4 and here the design ratio is bigger than 1, then also the design check is not fulfilled. But if the design ratio after step 4 is still below 1, then we can proceed with the last step. And this last step would be the interaction between normal force N and bending moment My. So these two internal forces are still missing from the steps before. And the reason why we cannot consider them together in step 4, because also these two internal forces will lead to normal stresses. And the reason why we cannot consider them together is because there's not a closed impression or not a simple formula to consider all these internal forces together. So, and what we will have to do as an alternative is we have to do this interaction. That means, we have multiple cases that we need to consider. And if you would visualize this interaction, you would receive such a diagram like shown here on the right. So we have our, let's say, our coordinate system with bending moment and normal force. And we have different cases in different areas which we have to consider. So you can see case 1 max, case 2 max, case 3 max. And also for a negative bending moment, we have these 3 cases for min. Yeah. And now we have to find out in which of these cases we are located. This can be found out based on the normal force and the bending moment. So we have a design bending moment and a design normal forces, and these two together will lead to a location here on this graph. And the last thing we will have to do is to find out if we are inside of this area or if we are outside of this area. If we are inside, then our design check of the PIFM is finally fulfilled and everything is okay. If we are outside, then it's not fulfilled and the design ratio will be higher than 1 or also higher than 100%. Yeah, and that's basically it. That's the idea of the PIFM with redistribution. And that's how it works. And you can, as I said, split it in 5 basic steps. Good. Before we switch to RFEM 6, we need to clarify one more thing, and that would be the limits of application. To figure these limits out, I have prepared 2 tables which show in which cases we can use the PIFM and also in which cases we can or cannot use the cross-section design checks. I'm always talking about the plastic cross-section design checks with these interaction formulas. The first table is about the cross-sections. So here we will see for which cross-sections or cross-section geometries the methods will work. And before we can have a look at the table, it's necessary to clarify these methods. So I think cross-section design checks according to Eurocode 3, that's clear. Also PIFM with redistribution is clear because that's exactly what we talked about some seconds ago. But we can also see 2 more methods in this table, which would be the PIFM without redistribution and the simplex method. So I want to leave a few words about these 2 methods. PIFM without redistribution is basically the same like PIFM with, but if we reach the maximum allowable stress, which would be the yield strength in one rectangular section part. So let me go back to this image here. So if one section part, like for example, the upper flange is completely utilized with the yield strength or has completely reached the yield strength in all locations, then the PIFM without redistribution is has reached its maximum. So then the design ratio of this PIFM with redistribution is 100% and we cannot proceed. So then it's over here. The PIFM with redistribution allows to transfer stresses from one section part to another section part. So this means if we reach the yield strength in one section part, this stress can be transferred to another section part. So this means that we have a bit bigger reserves with this method, or with other words, the utilization with the PIFM with redistribution will probably be a little bit less than for the PIFM without redistribution. Simplex method. Simplex basically does not have to do anything with PIFM. This is just a numerical optimization algorithm that can be used for different problems in technical aspects. And here we also use it together with the PIFM. And the simplex method works like this. It splits the whole cross-section in many small parts or small areas. And for each area, the internal forces, or you could also say the stresses, will be multiplied with a factor until the yield strength is reached. And that's done for each area. And by that, we can calculate or determine the cross-sectional capacity. So it's similar to the PIFM methods. Okay, now let's dive into this table and see for which cross-section we can use these methods. First of all, what is necessary? We need thin-walled cross-sections. So steel design does not work for massive cross-section, especially not the plastic design. The manufacturing type, here we can see that most manufacturing types are supported by most methods. So hot rolled, cold formed, and welded is all possible. There's one exception, and that is for the PIFM with redistribution. This is not permitted for cold formed profiles. So in this case, you would have to switch to the PIFM without redistribution or the simplex method, or you can also use the EC3 design checks. And if we now look at the cross-section category, or you could also say at the cross-section geometry, then we can see for Eurocode, there are some restrictions. So for cross-sections with 2 or 3 orthogonal elements, I gave some examples here. The EC3 plastic interaction formulas come to their limit because they are only regulated for a small variety of cross-sections, which would be hollow sections, circular and rectangular, and double T, like IPE profiles. Everything else is not regulated. So for everything else, you would have to do the linear interaction or even the elastic design of stresses. And that's not what we want to consider now, because we want to do an economical design check, which would mean that we have to do a plastic design. And the methods that are given by the Eurocode would be relatively conservative in this case. If we have more than 3 elements, we can also see that Eurocode 3 comes to its limit, because, as I said, only some cross sections are allowed for the really economical plastic design. And same for elements with non-orthogonal elements. So, or for cross sections with non-orthogonal elements, they are also not regulated for the plastic interaction formulas. For the PIFM, we can see, first of all, for the PIFM with redistribution, we have 2 conditions to be able to use this. The first condition is that we need a cross-section which consists of 2 or 3 orthogonal elements, like upper flange, web, lower flange, or also only 2 elements like upper flange and web. There's a special solution for hollow sections. So hollow sections can also be considered with the PIFM with redistribution. If we have more than 3 elements, like for example, this C profile, it has 5 elements, then we cannot use the PIFM with redistribution. Same thing if we have non-orthogonal elements, like for the 60-degree angle. So it's necessary that our elements are always orthogonal, so horizontal or vertical. If we are facing one of these restrictions, we have the possibility to switch to PIFM without redistribution, which is a bit less economical, but can still be more economical than the EC3 design checks, or the simplex method, which would be basically, relatively similar. And here we see there's no cross-section restriction at all, so we can perform the plastic design for every cross-section geometry that you could imagine, except massive cross-sections. Okay, that's it for the cross-sections. Now let's have a look at the application limits for internal forces. I think this table will be much easier to understand because we can see for the PIFM with or without redistribution and also the simplex method, there's no restriction at all. We can do the design for all cases of internal forces. They can all be applied at the same time on a cross-section, and we can still perform these design checks here. While for the EC3 design checks, again, plastic design checks with interaction formulas, there's a restriction. So here we cannot consider the torsional moments caused by primary torsion or also caused by warping torsion and the secondary torsional moment. So here we would have to switch back to the elastic design checks, which of course is much less economical. So this is definitely a big benefit, which speaks for the PIFM. Good. Now, when we talked about the application limits, we want finally switch to RFEM 6 and have a look how we can use the PIFM in the software. To show you that, I have already prepared this model here, which is a sign bridge for the highway. So you can imagine some cars driving under this bridge and some signs here on this bridge. We also have a small platform area where people can stand on and bring on new signs or remove some signs, for example. I don't want to show how I'm modeling the structure. We just want to have a look at the design. But on the other hand side, I will give you a small overview about this model so that you get a feeling for it. So let's see what we have here. First of all, for the cross-sections, we have a good variety of different cross-sections. That's also the reason why I choose such a model. So I wanted to have a practical project, which is a whole model so that we can see the impact and the effect of the PIFM on a real system, which could be a realistic project for some company. And I also choose this system because here I was able to use many different types of cross-sections. So also again that we can see the impact and everything better for the PIFM. For the cross-sections, we have square hollow sections for the columns here. We have angle profiles for the truss between the columns. For this truss member here, where the signs are located on, we have two different sizes of circular hollow sections. And then we have this secondary construction for the signs, which is made out of IPE profiles. And then we also have these C profiles. Maybe you can imagine that we need some surface here so that people can step and walk on it. There are also two load transfer surfaces in the system. They don't have any stiffness, so they are just there to transfer the loads that I have applied on these surfaces to the member structure which is below the surface. Yeah, so one surface for the wind loads and for the equipment loads, and one surface for the man load. Okay, that's the system. Load cases, we have self-weight. I think that's self-explaining. We have two wind load cases, which I calculated with the wind simulation of R-wind. So one is wind in Y direction, one is wind in X direction. Then we have our imposed load by people standing on this platform. I assume this load with 1 kilonewton per square meters in vertical direction. And last but not least, we have the equipment load, which is a vertical load on this load transfer surface here. And here I assumed a surface load of 0.5 kilonewton per square meter. I also considered two imperfection cases, but I don't want to go into detail too much for these imperfection. It's just a really basic local imperfection in two directions. Of course, if this would be a real project, I'm relatively sure that we would need to consider more imperfection cases and pay more attention to the imperfection. But for this case, this should be enough because we, in first point, we want to have a look at the PIFM. Yeah, and we also have the load combinations based on the combinatorics for these load cases. What I should also show you is that I activated the add-on torsional warping. So we are calculating with a 7th degree of freedom system. So we will receive all internal forces for this 7DOF system. And of course, what is important, I also activated the steel design add-on, which is necessary to perform the PIFM. And one last thing, I think that's relatively obvious, but I will show it nevertheless. For all load combinations, we are using second order theory. So we are calculating the internal forces on the deformed structure. Good. Now let's have a look at the design. For that, I will switch to the steel design add-on. And what I did here is I went to the global settings of the steel design and deactivated everything except the ultimate design configuration. Because for the PIFM, we only want to have a look at the ultimate limit state. Serviceability and fire resistance is not of interesting for this webinar here. But of course, for a real project, this would also be necessary to consider. Good. So if we want to use the PIFM now, we will have to create a new ultimate configuration and assign this configuration to our members. So we will right-click and say New Ultimate Configuration. And we can name this configuration PIFM with redistribution. And of course, if I already name it like this, we will do the setting so that the PIFM with redistribution will be performed for all assigned members. Before that, I want to do a small explanation for the topic stability. If you do the PIFM, you still have to do stability design checks. So it's still necessary to check for stability. But if you activate the PIFM, which would be this checkbox here, so perform advanced plastic design means the PIFM method, then you will receive a message which says if the advanced plastic design, this is PIFM, is activated for an object, the stability design will not be performed for that object. That means even if you let the stability design activated, it won't be performed for a member which is designed according to the PIFM. This is important to notice. Yeah, you should always have this in mind. But this does not mean, as I said, that you don't need to perform stability design. This is still necessary. It's just not possible with RFEM 6 because we are missing some information for the stability design we only can receive from the EC3 design checks. My recommendation to handle stability together with PIFM is to use the equivalent imperfection method for stability. This method means that I don't have to do stability design according to the standard, like equivalent member method or general method. I just model and calculate the structure in such a way that is so realistic that I can do the stability design together with the cross-section design. And yeah, this is the equivalent imperfection method. And if we want to use this, there are some conditions that we have to fulfill. The first condition is that we have to calculate according second order theory. I showed you that the load combinations use second order theory, so that condition is fulfilled. Second condition is that we need to activate the torsional warping add-on. So we need to calculate on a 7 degree of freedom system. And as I showed you, also this condition is already fulfilled in the system. Then we have the condition that we need to consider imperfections, local and global ones. And also that is something I have already considered with these two imperfection cases. But as I already mentioned, it's we would have to do this in more detail if this would be a real project. But yeah, for the moment, we will take this as it is and say, okay, imperfection is considered correctly. And the last thing we have to do is to activate this checkbox here, which says use gamma M1 for determination of the section resistance, because we do the stability analysis together with the section resistance. But this, on the other hand side, means that we have to use the partial safety factor for stability also for the section checks, which would be the PIFM in this case. So, and once we have considered all these conditions, we can deactivate the checkbox perform stability design, because now we are considering stability together with the advanced plastic design. Or in general with the cross-section design checks. I think that's better to say it like this. Okay, so now to the PIFM. As I already mentioned, we have to activate this checkbox to perform cross-section design checks with the PIFM. And as you can already see, if I activate this checkbox, we get such a new tab which says members plasticity. And this is the place where the magic happens. So here we have all our options for the PIFM. First option is that we can decide for which cross-section classes we want to allow the use of the PIFM. Default value is sections of class 1 and 2, and there's a strong recommendation from my side to always let this first option activated and not use the second one. It is possible to allow the PIFM for cross-sections of all classes, but you should know that this means that you will do the plastic, or you will do a plastic design check even for sections of class 3 and 4. And this is not permitted according to most standards, or I think to all standards that I know. So this is more like for testing purposes, and theoretically, or the method can also be used for cross sections of class 3 and 4. But if you want to do the design according to the standard, you will always use the first option, sections of class 1 and 2 only. Next option that we have is we can use one of these three mentioned methods, which would be the PIFM with redistribution, the PIFM without redistribution, and the simplex method. And last but not least, there's one more setting which says use constant shear stress for circular hollow sections. And I think that's self-explaining, so it does exactly what it says. If we have this option activated, then we will always receive a constant shear stress if we are inside of a circular hollow section. I will leave this option activated like it is on default, but of course you can also deactivate it if you want. Okay, I said for this first ultimate configuration, we want to use the PIFM with redistribution. So we have already the correct options chosen here. So here we have the PIFM with redistribution activated. Now we can assign this ultimate configuration to our whole structure in the first instance. Apply, and yeah, now we are basically ready to go and can start the calculation. In the meantime, we will switch back to the PowerPoint presentation and we will go back to this slide here. And probably you already have noticed a problem that we will face once the calculation have finished. And that is, we have used the PIFM with redistribution, but we also have cold formed cross sections in our structure, which would be the square hollow section of the columns and also the Z profile. So in this case, we will probably receive a warning message or an error because here the PIFM with redistribution cannot be used. Okay, so hopefully the calculation has finished in the meantime. And yeah, okay, this looks good. So now we have the results of the steel design. Let me go to the table design ratios on members and then to the subtable design ratios by cross section. And as I already said, we have exactly this problem for the square hollow sections. The design check says, okay, the section is not allowed for PIFM with redistribution, so we have to switch the method. Here it also says that we have a problem with the warping on a hollow section, so this is not allowed for the design because it's a hollow section. I tested it before and I know that the amount of the warping torsion, so we can increase the limit so that the warping will be ignored for the hollow section and then the design will be performed without any error. Of course, this limit value has a reason and it should not in every case be increased without thinking about it. But in this case, I can say, okay, I have this the square hollow section, and I will assume that it is warping free. So because of the cross-section geometry. The angle profile shows both. So it shows the PIFM, so advanced plastic design on the one hand side, but there are also locations where the PIFM could not be performed and instead the section proof according to Eurocode has to be done. The reason for that is that such an angle profile is always cross-section class 3 or 4. So if we go to the design check details, we can see, okay, it's classified as class 3, and in this case, the PIFM cannot be used. So RFEM 6 automatically switches to the EC3 design checks, which is a good thing in my opinion. For some cases, the cross-section is not classified as class 3 or 4, and these are especially the cases where we don't have any compression, so then we can still do the PIFM. For the circular hollow sections, everything looks okay. Advanced plastic designs, or PIFM, is used here. Also for the IPE profile, no problem. And yeah, for the C shape section, we can see that the PIFM could not be performed. And for every location, the solver or RFEM has automatically switched to the section proof, but that's okay. We can do the section proof according EC3. That's still okay. But we can also see that we have a little bit too high design ratio here, so probably it would be necessary to increase the cross-section size for this cross-section. Okay, now let's get rid of these two problems here. So we will create a new ultimate configuration. And this time we want to use the PIFM without redistribution. Maybe let me do it different. I will delete this new one and just copy the existing one. So we have the same options already activated, which is good. And just give it a different name without redistribution. So for the members plasticity tab, of course, we will have to switch the method. So I will switch to a partial internal forces method without redistribution. And here we receive one additional option, which I did not mention before. And this is the limit of width to thickness ratio of section elements. If one section element in our whole design is below this limit value, LT, then we will receive a warning and the design cannot be performed. The reason for this warning is that, and I did not mention that before, but I will mention it now. The reason for that is that each section part receives only internal forces for bending moment about the strong axis. So this is just an assumption, for modeling, which makes it easier to calculate. But in this case, for example, the bending moment MZ, which would be about this axis here, only the upper and the lower flange would receive partial internal forces caused by the bending moment MZ, and the bending moment MY is completely taken by the web. So that's just a simplification that is used for the PIFM. And this is also okay. We can go with this simplification, but if we have relatively massive rectangular section parts, so for example, if the thickness of the flanges are much higher, then of course the simplification is not that exact anymore, because then each section part can take bending moment in both directions, and this is not considered in the PIFM, so we will receive this warning message. If you receive this warning message, you have two options. You can lower this value. Of course, you should know what you are doing, so that's the reason why I gave this explanation. The other case would be to switch back to the EC3 design checks, because then it does not matter. Or you can use another method, because this limit is only relevant for the PIFM without redistribution. For the PIFM with redistribution, the double bending can be considered for each sectional element, and also for the simplex method. Okay, and also we have to increase the limit value for torsion, as I mentioned, for warping torsion, as I mentioned before. And because I tested this before, of course, then I know that I have to increase this value to 6%, and then we will be rid of this warning message. Okay, and before I apply, we will have to assign this new configuration for our square hollow sections. So I will select the square hollow section here in the navigator, and it automatically selects all members with this cross section. So you can apply and okay. And now we can do the calculation again. All right, now the calculation of steel design add-on has finished. And if we have a look again at our design ratios by cross-section, we can now see that the square hollow sections has also performed, or for the square hollow sections, also the PIFM has been used, but in this case without redistribution, and for the other sections, everything stayed the same. One more thing I would like to show in RFEM 6 are the design check details of these PIFM design checks. For that, I will have we want to have a look together as an example to the IPE profile. So I will double click on the design check with the highest design ratio. And now we will see what has been done for this member on this location for one especially load combination. And what we can see, not only one design check has been performed for the PIFM, but multiple design checks. And reason for that is because these steps that I mentioned before, if we go back to this slide here, we have these 5 steps. They are done individually, especially step 3, 4, and 5. So the verification of shear internal forces, verification of normal stress internal forces, and the interaction. So for each of these 3 steps, we have a separate design check. And also for each section part, we have a several design check. And you will see this here. First of all, we have these shear design checks for the top flange, for the web, and for the bottom flange. Then we have the normal stress design check, which is only performed for the top flange and the bottom flange. And in this case, it's called bending moment, because here we only consider the internal forces that lead to a bending moment in these 2 flanges. And last but not least, we have the interaction, which is done once for the axial force and once for the bending moment. And this again is done on the whole section. So let's go through it on the example of the top flange for this section. And if we have a look at the formulas of this design check, maybe I can make it a bit bigger, then we can see different things. First of all, we see the transformation of internal forces from the original to the reference coordinate system. This is always when you see this line above the internal force. So here we have our trigonometric functions, which are used to convert these internal forces into our reference coordinate system. This is always done for the required internal forces, which are required for this special design check here. In the next step, we can see the conversion from our reference internal forces to the partial internal forces. So now we receive, for example, the shear force for our upper flange. So this O stands for the upper flange in this case. And as I already said before, the equilibrium conditions are used to calculate these partial internal forces. Again, this is done for all internal forces that are required for this particular design check. And yeah, we can already scroll down to the bottom. And the last thing that is interesting here is the final design check for the shear forces. Yeah, I would say we will have to take this formula as it is. So there is a derivation for this formula, but it is really complex and long and time consuming to talk about this. So this won't be a topic for this webinar. So we just take this formula as it is. And the result, what we receive from the shear design check is the design check ratio. So in this case, we have 0.4%. And maybe please remember to this expression, because this is the, this will be important for the next design check, which would be the bending moment for the top flange. Again, transformation of internal forces, calculation of partial internal forces. And now this is the important part, our reduction of the yield strength based on this expression from the design check before. So in this case, we have only a really small reduction because we had a design check ratio here about 0.4%, but of course the reduction can be bigger. So, and with this reduced yield strength, we do the design check for the bending moment. Again, with this final design check equation, and now we already receive a design check ratio of 12.9%. And with that, we can finally go to the interaction formula. And what we can see here, if we scroll down a little bit, is that RFEM detects that we are located in case 2. Yeah, you can see this here in the references. So only case 2 is considered, because now we already know that we are in this case in the interaction diagram. And for this case, the minimum and the maximum allowable bending moment is calculated based on our normal forces. And the last thing we have to do is to check if our design bending moment is located between these two limits here. And that's basically what is done in this last design check. So our bending moment is minus 2.6 kilonewton meters, and our minimum allowable bending moment is minus 5, and the maximum one is plus 5. So we are definitely located between these limits. So our final design check is fulfilled with 52% utilization. And that's basically it. That's exactly what I tried to describe before with these 5 steps here. Okay, now let's have a look at our next content point for the webinar, which would be the comparison between PIFM and the EC3 design checks. To do this comparison, I have decided to perform the design checks for all these methods, and based on the structure I showed in RFEM 6. I did it separately for each cross section and always wrote down the maximum utilization for each cross section. If we do this according to the EC3 standards, we can always see that only elastic design is possible based on the application limits. So probably here the reason for the elastic design is on the one hand side that we have warping torsion in many cases. On the other hand side, that the cross section is not applicable for the plastic interaction formulas. So this, of course, is not a very positive aspect of the EC3 design checks. And if we compare this to the PIFM, to the different methods, we can see that in most cases we have a significant lower utilization compared to the EC3 design checks. So always the first value here in each cell is the utilization for this cross-section for each method. The second value is the reserve of this utilization compared to the EC3 design check. And as we can see, we have significant reserves if we use the plastic design and especially if we use the PIFM with redistribution. We can also see that in some cases, the PIFM can be less economical than the EC3 design checks. But as you can see, that's not the typical case. So in most cases, there's really a big advantage by the PIFM. And even for example, for these circular hollow sections, you can still see that there's at least one method you can use which will lead to more economical results, which means lower utilization compared to EC3 design checks. Of course, I'm always comparing plastic design for these three methods with, in this case, elastic design. And I think it's obvious that we have a much lower utilization if we compare elastic design to plastic design. But nevertheless, if you only design according EC3, you have no possibility to do the plastic design in these cases here. What has also to be mentioned is that for the angle profile and the C profile, of course, I can do the plastic design, but according to the standard, as I already mentioned, it would not be permitted because here we are not in cross-section class 1 and 2, so we are not allowed to do the plastic design. That means that for the angle profile and for the C profile, you would have to keep going with the EC3 design checks. Okay, so much to the comparison, and I think, from this point of view, it becomes much more clearer how beneficial the PIFM can be compared to the EC3 design checks. And I think in many cases, you will be able to reduce your cross-section size in 1 or 2 sizes, which of course will reduce the costs of the project and lead to a more economical structural analysis. Good. Last but not least, we have reached our last content point of the webinar, which would be the summary. And for the summary, I would like to clarify one last question or one final question, which is, when is the PIFM worth it? So now we have seen how the PIFM works. We have already seen how it can be used together with RFEM 6. But when should I really use this method? And when should I probably stay with the EC3 design checks? And here are my thoughts to this question, or my answers. First of all, of course, we need cross-sections that allow the utilization of plastic reserves. So for EC3 and also many other standards, this means we need cross-section class 1 or 2. Otherwise, we are not allowed to use the plastic reserves, and then PIFM is not worth it, so it cannot be used. Next point is PIFM is worth it if we have a highly variable stress distribution. To understand this sentence, please have a look at the image on the right side, the top image. If we have, for example, only a normal force in the cross-section, then we will receive a stress distribution like this. And as you can see, the complete cross-section can be utilized until the yield strength on every location. So we basically have no plastic reserves at all. In such a case, the PIFM won't be worth it. It will lead to the same design check ratios like if you do the elastic design according to the standard. But if there are multiple internal forces like combined normal force, bending, and maybe even biaxial bending, then you can see that not every part of the cross-section is utilized to the yield strength. And in this case, we have bigger plastic reserves, and the use of the PIFM will be worth it and lead to lower utilizations compared to the elastic design. PIFM is especially worth it if we have warping, bi-moment, and secondary torsion, because in this case, we are not able to perform the plastic design with the non-conservative interaction formulas according to the Eurocode 3. And yeah, PIFM can still be used. So with that method, we can still do an economical design, even if we have the warping, bi-moment, and secondary torsion. And last but not least, for special cross-section shapes, especially these cross-section shapes that do not allow the interaction according to Eurocode 3, 6.2.9 and 6.2.10. And yeah, as I mentioned before, for these interaction formulas, only double T profiles and hollow sections can be used. All other sections cannot be used together with these plastic interaction formulas, which means, for example, if we have rectangular hollow section with different thicknesses of the flanges and the webs, then we cannot use these formulas. So here also PIFM would be a good option. And also for some special profiles like PI profiles, Z profiles, but also U and T sections, which are both really very common cross sections and often used ones. Also for these cross sections, the PIFM is definitely worth it, because here we are finally able to do the plastic design. And yeah, the last thing I wanted to show you is this figure on the lower part of the slide here. And here again, we can see the plastic reserves compared to the elastic design. In this case, only for a rectangular hollow section. But remember, for the PIFM, we are only considering section parts that are rectangular. So yeah, this is basically it for the PIFM. And here again, we can see that the plastic reserves can be really big only for combined bending moment and normal force. If we have more internal forces, then this can even be higher than just for bending moment and normal force. But even already here, we can see that in some cases, we have such a big increase between elastic limit state of resistant and plastic limit state of resistant. And I think this, this area here should definitely be used to provide an economical design. So yeah, PIFM is definitely worth it in many cases. And yeah, I hope that I could show you that it can lead to a better, or let's say a lower utilization in many cases. And yeah, so we have finished with the presentation. I hope that I could explain the method, that you get an idea about how it works, and also that you get an idea about how it can be used together with RFEM 6. And yeah, hopefully you will also use the PIFM in your future projects to save some costs and also do a much more economical plastic design. Okay, that was all for me, and I'm handing it back to Andreas.
Thank you, Niklas, for your presentation. At the end of the webinar, I have an additional hint to our online courses. There's the RFEM 6 course. That's a course for beginners. Then the Eurocode 2 course for the concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design, and the Eurocode 8 course for the earthquake design. For more information and prices, just scan the QR codes or press at the links here. You can get such a course for free when you submit your customer project on our website. You can also write me an email to info@dlubal.com. I will write you back what files I need. But you can also download or upload the files when you scan the QR code or click at the link. And the courses are valued at 199 to 399 euros. Then a hint to our free online services. There's, for example, the Dlubal community. You can ask questions there. Then there's the geozone tool for the determination of snow, wind, and earthquake loads. You can determine cross-section properties on our website, download 3D models, for example, as a template for your project. And of course, you can download the 90-day trial versions of RFEM 6, RSTAB 9, RWind 3, or RSection. You can find more information on our website, for example, the recorded webinars, the knowledge base articles. You can ask our AI assistant, Mia, all the time. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Niklas for the presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.